Hello everyone, my name is Ethan, and today I invite everyone to explore the puzzle I have here. So the puzzle is how many 5-digit integers exist where the digits are non-increasing from left to right. Now, upon first glance, what we might be tempted to think, or at least what I'm tempted to think, is split it into a lot of different cases, right? What if there's 5 distinct digits? What if 2 digits are the same and the other 3 are different? What if 3 digits are the same and the other 2 are different, right? I might be tempted to split it up into all these different cases. But as a general rule of thumb, casework is painful. So today, I invite you all to explore sort of a construction argument that bypasses all this casework and still arrives at the desired result. So let's get to it. Okay, so here, 98851, these digits are non-increasing from left to right. So this is an example of one of the 5-digit integers that we want. Now, I claim that on the right-hand side, I have something that I call a pebbles in the digit cups construction. Now, I claim that every non-increasing 5-digit number corresponds to one unique pebbles in the cup construction. Now, let me explain why this is the case. First, let's show why this direction is true. Why, if given a 5-digit non-increasing number from left to right, I can always go into this pebbles in the cup construction. So first, let me explain what this pebbles of a cup construction really means. Essentially, we have 10 different digit cups labeled from 9, 8, 7, all the way down to 0. And in each of these digit cups, there might be some number of pebbles. And so the idea is if I have this number 98851, then I can look at the digits from the left to the right. And I start with the leading digit 9. I want to sort of pick up this 9, turn it into a pebble, and drop it into the digit cup labeled 9. And I want to turn these two 8s into 2 different pebbles, and then drop the 2 pebbles into the digit cup labeled 8. And here I see a 5. Then I turn this 5 into a pebble and drop it into the digit cup labeled 5. Similarly, here, if I have a 1, imagine turning this 1 to a pebble and dropping it to the cup labeled 1. So this is how I go from the left to the right. Now, what if I'm given a construction on the right-hand side and I'm asked to reverse this to get a 5-digit integer that's non-increasing from left to right? Well, again, we look at this from left to right. Start with a bucket labeled 9. Imagine pulling out the pebble this time. And as you pull out the pebble, imagine that some magical force turns that pebble into the digit 9. Similarly, there's 2 pebbles in the bucket labeled 8. Imagine pulling out these pebbles, these 2 pebbles in 8, and magically turning them into the numbers 8 and 8. Do the same for 5 and 1. Pull the pebble out of the digit cup and turn that pebble into the digit of that digit cup. And then in the end, if we make the order of this from left to right, then we get our digits. Then we get that our digits are non-increasing from left to right. And sort of when we read these numbers from left to right, we get exactly the number on the left-hand side, which is our desired 5-digit integer. So we sort of see the intuition that this pebbles to the digit cups construction is really equivalent to this 5-digit non-increasing integer right here. So then now the question becomes, how can we count this construction on the right-hand side? Because the left-hand side, counting the left-hand side is the problem. And it's not very obvious how I can count this efficiently. But if the construction on the right-hand side is equivalent to that on the left, and if this is easier to count, then maybe we can count it via this construction on the right-hand side. So essentially what I really have is, if I label the number of pebbles in the digit cup labeled 0 as x0, I let the number of pebbles in the digit cup labeled 1 as x to be x1, and then in the end, I get that x0 plus x1 plus x2 plus all the way up to x9 is equal to 5. Essentially what this statement says is that the sum of the number of pebbles across each different cup is equal to 5. And that is true because we have a 5-digit number, right? Which means that we should have 5 different pebbles in total. And here, each of x0, x1, x2, all the way up to x9 should be non-negative integers, because a cup can be empty, which could contain 0 pebbles, or it could contain a positive integer number of pebbles. So these are all non-negative and they sum up to 5. Is it very obvious how we can count this? Still not quite obvious, right? So we lean back into this construction. Now I add a new definition here, which is something called a divider. Do you see the right-hand side of the cup labeled 9, and do you see the left-hand side of the cup labeled 8? Let us combine these two edges together to form what I call a divider. And if we count, there are a total of 10 cups, so there are a total of 9 different dividers in between. And so in the end, what I'm really trying to do is I have 5 pebbles and I have 9 dividers, so a total of 14 objects. And what we can do is we have 14 different free slots for us to arrange these objects. Notice that we don't have any constraints when it comes to arranging the pebbles and the dividers, because at the end of the day, if 2 dividers, there's nothing between the 2 dividers, then that means there's nothing in the cup between the 2 dividers. If there is some pebble or some amount of pebbles between 2 dividers, then that just corresponds to the number of pebbles in that cup between the 2 dividers. So really, we are counting how many ways we can arrange the 5 rocks and the 9 dividers on 14 different slots and positions. Now, one way that we can do that is we can first let each of these 5 pebbles go to 5 of the 14 positions, and then we know that the rest of the 9 positions must be occupied by dividers. And so how do we count that? Well, that is essentially just 14 choose 5 ways that we can do so, because there's 14 different positions and there's 5 positions that these 5 pebbles can go into. Now let us compute 14 choose 5. It's just 14 times 13 times 12 times 11 times 10 divided by 5 times 4 times 3 times 2 times 1. Now we can do some clever cancellation here. We know that 12 is 4 times 3, so this cancels. We also know that 10 equals 5 times 2, and also times 1, I guess. So this also cancels. So in the end, we're left with 14 times 13 times 11, which we find to be 2002. But now you might ask, are we really done here? The answer is no. Why? Because there is something that we missed. Consider 0, 0, 0, 0, 0, right? 5 zeros. Can that be a valid 5-digit integer? No. So we must exclude that. After we exclude this construction, if the number is not 0, 0, 0, 0, 0, and it's non-increasing from left to right, then we know that the leading digit must be at least 1. Oh, so I know now. Only this 5-digit number is an invalid construction. So what we really have is a total of 2002 minus 1, which is a total of 2001 total valid 5-digit integers that's non-increasing from left to right. Thank you so much for watching, and thank you so much for participating in solving this puzzle together with me.